We're going to talk about Kepler's laws of planetary motion. The first law is that planets move in elliptical orbits with the sun at one focus. Uh, Before this, people just assumed planets revolved in circles or orbited in circular paths, and that's not exactly true. Kepler came up with the idea that they were actually moving in elliptical orbits with the sun at one focus. And just to remind us what an ellipse looks like, the way you draw an ellipse, start the video again. You have two foci, and if you tighten the string that's loosely attached to both foci, and you trace the path, what you'll get is an ellipse. Excuse my clumsiness here, but we trace the path with the two foci around the tightened string. And what you're left with is, there we go. What you're left with is an ellipse. You can see the path that my chalk mark made is the ellipse, and if you look at the foci, you've got a foci right here, a foci right here, and the path that the ellipse made. A little difficult to see, but here is the line when you keep it in focus. The smiley face comes because that's the loose string, and that's what we use to trace the path. You can see the ellipse and the two foci, and that's how you create an ellipse. And what a circle is, if you collapse these foci down to one single point, that that would create a circle if we did the same activity. And that's what makes a special type of ellipse. So, getting back to uh, Kepler's law of planetary motion, his first law, planets move in this ellipse with the sun at one focus. Okay, so here's an ellipse, the sun is at one focus. Okay, and the planet here in gray is moving along this elliptical path. A couple of things you may want to know is are the fact that at the other ellipse there's nothing. At that opposite focus, there's nothing there. Uh, the other thing is that the sun's going to be at the perihelion, and over here, the opposite end of the ellipse is what we call the aphelion. Perihelion is next to the sun. Aphelion is away from the sun. So, elliptical orbit, big part of Kepler's laws of planetary motion. It's the first law. And if I have a planet simulator from FIT, Colorado, uh, Colorado University, and if I start this, you can see the elliptical orbit of the planet around the sun. It takes its elliptical orbit. And after we're done, we can see the ellipse. Kepler's second law is called the law of areas, and what it says is that if you had a line that connected the planet to the sun, it would sweep out equal areas in equal times. Uh, and the reason why, and that's why they call it the law of areas. It's a little hard to visualize this without a picture, so I have a picture here for Kepler's second law. And what you have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 months to orbit for the Earth to orbit around the sun. So these are equal time periods. Each one represents a month. So from G to H, this area in here is equal to the area from I to H, or from H to I. It's still 1 month of time, but this line that's connected to the planet is going to sweep out equal areas for each month. And any time interval you do, it's going to have the same equal areas. So I to H and A to B, it's still 1 month of travel, still 1 month of travel, and these areas are equivalent. These areas are equal. Law of equal areas. If we go back to our simulator and we watch our simulator move, we should notice a few things and you know why those areas look different. Uh, and one of the things we should notice is the relative speed that this is taking around the sun. Uh, and if we paused it and slowed this down, we would see that in the first two time periods for this planet, if I traced out its path, after whatever you want to call it, after 2 months, this is how far it's gone. Uh, in the next 2 month time period, from 2 to 4 seconds, here's its path. Same time period has an even longer path, and then the path starts to get short again, after the 12 months. So what you're witnessing here is the fact that because of this law of areas, we can make we can make the observation that as the planet gets closer to the sun or to the perihelion, it's going to speed up. The closer it gets to the perihelion, it's going to speed up and get faster and faster until it gets around the sun, and then it slows down slower and slower. Its slowest point is at the opposite foci at the aphelion point. Kepler's third law is a ratio. Uh, it's also called the law of periods. And it says that the square of the period of any planet is proportional to the cube of the distance between that planet and the sun. So your period squared over your radius squared is going to be equal to some constant. Some people write it like this and call that the Kepler's constant. Some people you'll see write like this, where they'll have r cubed over t cubed is some constant. Either way, this ratio between the period and the distance between the planet and the sun is going to be equal to some constant. So if we have the same solar system, the ratio of the squares of the periods for any two planets is equal to the ratio of the cubes uh, of their distances to the objects that they're orbiting. So if we, took the period of the Earth, so the period of Earth squared over the radius from the sun to the Earth cubed is equal to some constant. Well, any other planet in Earth's solar system is going to be equal to this same constant. So we can say that the period of any other planet, P, just call it planet P, over 2 is going to be over the radius between the sun and that planet P. They're going to be equal. Another way to write this is to just cross multiply it out. And you get the period squared, the ratios of the period squared is equal to the ratio of the radii squared. one thing to note about Kepler's laws is that they work for uh, both planets orbiting suns. They also work for satellites orbiting planets. Uh, so anything that's orbiting a larger body uh, in planetary orbit or in satellite orbit is going to abide by these Kepler's laws. Uh, and just a little bit about satellite orbits. Any object that's orbiting another object is considered to be a satellite. So you got Earth, that's a satellite of the sun. The moon we consider a satellite of the Earth. Uh, and just to kind of go back to what I was talking about with the fact that satellites just obey the laws of Kepler. Here's a graph of orbital periods for all the planets and their major axis. You can see the straight line path it takes. And here we have the four largest of Jupiter's moons, or what we're defining as satellites. They're going to have the same ratios in comparison to Jupiter being the main object that they orbit. Another thing we need to note is the fact that the satellite stays in orbit around uh, another object due to the gravitational force. This gravitational force is a centripetal force that's keeping the object in circular orbit or an elliptical orbit. That is the center-seeking force. And if we're assuming that this object is traveling in uniform motion, any satellite, if we wanted to know the period of the satellite, well, we can do a derivation. Force of gravity is gravitational constant times mass of the small object times the mass of the big object over the radius squared. Well, that force of gravity that's acting on the little object is defined by the centripetal force, which is MAC. Therefore, the little mass cancels out. Gm over r squared is equal to your centripetal acceleration. And centripetal acceleration is equal to v squared over r. And therefore, if you do a bit of algebra, you'll see that v squared is equal to gm over r. Another way to write that is take the square root of both sides. Your velocity, uniform velocity of your satellite orbit, or the magnitude, is going to be equal to g gravitational constant times the mass of what you're orbiting over the radius between the centers. And if we remember what velocity is equal to, velocity is your circumference, 2 pi r over your period, and we're trying to define the period. So I'm going to square both things just so I don't have to work with the square root symbol. Square both sides, you'll get 4 pi squared r squared over t squared equals capital G, capital M over r. Reworking this to get t squared. T squared, the period is going to be defined by 4 pi squared times the radius between the centers cubed over gravitational constant and the mass of what's being orbited. If we take the square root of both sides, uh, you can find we can find that t is just the square root of that 4 pi squared r cubed over g m, and there's your derived formula for the period. One thing to note is if we look at this formula here and we move things around a bit, we can take the r cubed over here, and what formula do we get? T squared, the period squared, over the radius cubed is equal to 4 pi squared over g m. The period squared over r squared is equal to some constant, which goes back to Newton or Kepler's third law. This formula here will work for periods for any satellite orbiting a larger body. So will this velocity, as long as uh, you're staying consistent with, the radius between the two objects and the planet or sun that you're orbiting.